In this segment, we're going to finish up our consideration of the particle in a box. First up, we're going to take a look at how well the particle in a box model might do at describing an actual atom. All right, and so as you might guess, an atom is not really a one-dimensional box, so the answer to that question is actually not that great, probably in this case, but we'll do a calculation to see that, okay? When an atom emits or absorbs a photon, what it's doing is changing energy states, right? So the photon that's absorbed or emitted, its energy is going to correspond to the difference in energy between two quantum states, right? So if I'm doing absorption, on the top figure here, energy is increasing going up on the screen, right? Down here, I have my atom sitting in its, let's say it's in the ground state energy level. If it's a hydrogen atom, that's the hydrogen 1s orbital, right? If my hydrogen atom absorbs a photon, the electron is going to be promoted to some higher energy orbital, right? 2s, 2p, whatever it happens to be, okay? And so in doing that, the energy of the electron is going to go up. The photon energy is going to be the amount of energy that the atom picks up, right? Because the atom's absorbing the photon is destroyed in this process, or consumed, whatever kind of word you like, and the energy has to be conserved, and so the energy goes to the atom. So h nu here corresponds to the length of this arrow that gets me between there. Right? The same transition could happen in the opposite direction if my atom somehow started off up here, if my electron started in an excited state, right? So if I found a hydrogen atom that happened to have its electron hanging out in a 2p orbital, say, then that atom would want to lose some energy to get to the ground state configuration, and it would then be able to emit a photon. In this case, I would draw an arrow pointing down, I guess, that corresponds to emitting the photon. If these are the same two states, the same frequency or wavelength of light would be involved in both of them. It's just a question of the directionality, right? The emission version of this is something that a lot of us that teach freshman chem often do as a demonstration, right? Where we have a set of different tubes filled with gases that we can snap into a power supply and light them up. And if you're wearing diffraction grating glasses, you can see the different wavelengths separate out, or the different colors of light that are being emitted when that happens. So what are we going to do? We're going to take our hydrogen atom. We're going to assume the hydrogen atom can be labeled as a box of length 2a0. A0, remember, is that Bohr radius, that 53 picometer number, which is sort of the most probable value of the radius for the hydrogen atom, right? So 2a0 would correspond to something like a diameter of the atom. We're going to find what wavelength of light will be absorbed or emitted in a transition between the n equals 1 and n equals 2 levels, okay? So I'm going to imagine that down here I say that my lower state is n equals 1, my upper state is n equals 2, and I'm going to find the wavelength of light. So I'm going to start off by finding the energy difference between those two states, because that's what's going to get me towards the wavelength, or to the frequency or the wavelength, whichever I care for, okay? We know our energies look like this. The energy of each level is just n squared h squared over 8ml squared. We want this difference in energy, right? And we have L equal to 2a0, because that's what it said in our description. So if I want to get E2 minus E1, that's the quantity I want. That's going to be equal to just, well, let's see, 2 squared minus 1 squared for the n squared piece. And then both of those have h squared over 8ml squared, right? L squared is 4a0 squared. So the first piece out there is what? Is 4 minus 1, so that's 3. So I've got 3h squared on top. Down here, I've got an 8 there, and my L squared, because L is 2a0, so L squared is 4a0 squared. So this is 32m times a0 squared, okay? So that is what delta E should be for this thing. So I'm going to go ahead and get the energy, I guess, first. And so that's equal to 3. I have Planck's constant. And that's squared. On the bottom, I've got 8. I've got the electron, no, I don't have 8 anymore, I'm sorry, I've got 32. I looked up at the wrong line up there. I've got 9.1 times 10 to the minus 31 in kilograms. I've got A0, which is about 53 picometers. In my notes, I've got a value that looks like this, 52.92 times 10 to the minus 11 meters. Right, picometers are 10 to the minus 12 meters, and so 53 is roughly that number. Multiply all that out, and I get 1.6 times 10 to the minus 17 joules, okay, which on the atomic scale, that's a reasonably, decently large energy, right? If I take that, I want to find that and make it into a wavelength, so I can say that the wavelength is equal to hc over E. So if I put those in, my speed of light, which is 3 times 10 to the 8th meters per second. And then my energy is that number we just calculated. And so if I multiply that one out, my notes say I get about 1.2 times 10 to the minus 8 meters. That would be about, what, 12 nanometers. The actual transition, I can tell you, the actual wavelength for this is about 121 nanometers. So what does that tell us? That tells us that our box model didn't work very well for this, right? And really, we took the one-dimensional box and applied it to something roughly the size of our three-dimensional atoms. So if we wanted to do a better job of that, we might have tried a particle in a three-dimensional box, which we'll actually look at how to do that a little bit later in this video. Or we could even have conjured up something a little stranger, like a particle trapped within a sphere. And if we did that, we would actually get a significantly better result in terms of trying to match the experimental value. But it does show us how we could begin to try and calculate a wavelength for a spectroscopic transition. And so there's some value in the calculation, even if the result is at odds with the actual experimental value. I said when introducing this topic that there were these quantum dots, which were one application of these things. And so this is something that, gosh, if we were meeting in person, I'd probably do this as one of those clicker questions or something like that. But the quantum dots are roughly spherical particles, but they act more or less like particles in a box, right? The quantum dot is the box. Here we've got the particles where we're looking at light being absorbed or emitted from them. I'm not sure about this, which way this picture is actually set up, but I've got red ones on one end and purple ones on the other. The question is which end corresponds to the smallest particles, right? To think about this, we could view this in terms of what we just did, really. And so if I flip back to this, notice that in my expression for the energy, I've got L squared on the bottom, right? And so as the particles get bigger, the energy corresponding to the transition would get smaller. As the particles get smaller, the energy should get bigger, right? And so, whoops, wrong direction. If I look at these, I guess I have to know that the blue and purple end of the spectrum is large photon energies or short wavelengths, and the red end are these small energies. Okay, and my delta E was supposed to get smaller when the particles were bigger, and that means that the blue and purple end of the array should be the ones that are the smaller particles, right? So my particles are small down here and large over here. Because that's what corresponds to shifting that particular energy spacing, right? Take that idea a little farther. If we make the box really big, if we take the length of the box and make it, instead of being a nanometer, make it like a kilometer, right? If we do that, then the spacing between the energy levels is going to get very, very, very small. Okay, that's why in macroscopic life you don't notice quantization. It's because there is effectively no meaningful separation between the energy levels. So you really can take on any energy because every energy you pick, there's an energy level there because the separations between them are vanishingly small in the macroscopic distance scale. Right. A little bit of consideration for for boxes rather of higher dimensionality. Right. I said that we would have done a better job on our hydrogen atom if we at least let it be 3-dimensional. Right. If we take a 2-dimensional box, we're going to have an X direction and a Y direction. We have those should be independent of each other. Right. The position along the X-axis and along the Y-axis should not be correlated. And that means you can essentially separate the problem into an X piece and a Y piece. If we do this, because we now have the X part of the problem and the Y part of the problem, the solutions are going to get to have 2 quantum numbers instead of 1, essentially 1 related to X and 1 related to Y. Other than that, it will work largely the same. Right? There's a bit of this worked through in the textbook. I'm not going to belabor it because I don't want to spend a lot of time on this this particular chunk of stuff, but it's worth a quick look. Right? If I allow for the possibility that the box is got different dimensions in the different sizes in the X and Y directions. Right? So right now A and B in there are both in the role of what used to be L, the length of the box. Right? Notice that my problem now has 2 different quantum numbers, which we've labeled here as nx and ny. Each one of those quantum numbers has to follow the same rule as the original n in the 1-dimensional problem, right? So it goes from 1, 2, 3, and so on. The form of the solution, the form of the, if I call this the x piece of the solution, and this the y piece, notice that they both look pretty much exactly like what we got for the 1-dimensional box. Right? And so if I take that and take the whole thing and put it together, we can get various forms for this. And this is the energy expression down here. Essentially, it just has 2 quantum numbers and 2 edge lengths to it because now it's got 2 dimensions going on. All right. Let's take the simplest version of the 2-dimensional box, and let's say we want to make the box be square. Okay, if I make the box be square, then A and B become equal, and in the energy expression there, what I've done is I've just replaced the A and B symbols. I've just replaced them both with L. Okay, because they're the same, then I can take and I can reduce this thing to just get to L squared there. Right. If I want to find the lowest possible energy, that's going to be where I have the smallest possible values of nx and ny. So they're both going to be equal to 1. Right. That's my ground state. And for that state, I would have this chunk of constants over here times my quantum number piece would be 1 squared plus 1 squared, so it would be 2, right? When I go up the ladder from there, an interesting thing happens. The next highest energy state is going to correspond to raising one or the other of the quantum numbers from 1 to 2, right? Because if I think of each one is allowed to have any integer value, right? So if I change just one of them, I'll go up by a smaller increment of energy. Because of that, I get my first look at what are known in quantum mechanic language as degenerate states. I honestly don't know why the word degenerate got chosen for this, but that is what is used for 2 states that have the same energy as one another, okay? In this case, in my energy level diagram, if this is just the say 1, 1 state, where those are the 2 quantum numbers, right? Then I could say maybe this one is 1, 2, and this one is 2, 1. Right. Next up would be 2, 2, and that one there's only one of because both quantum numbers are the same. Right. If I want to go higher than that, then I'm going to change one or the other quantum number up to 3. So I'd get 2, 3, and 3, 2, and so I'll get this sort of toggling between single states and degenerate states as I do this. If the idea of degenerate states seems odd to you, just think of, as I noted on the bottom of the slide there, what is the most familiar example to you is if you're drawing electron configurations, you have p orbitals, you know there's going to be 3 of them at the same energy, right? So you get your, say, px, py, pz, and you know that all 3 of those orbitals have the same energy unless the atom is hanging out in a magnetic field or something like that, right? This is just the same idea. It's just we get to have multiple quantum states that just happen essentially coincidentally to have the same sort of energy, right? So our energy diagram will get a bit more complicated looking as we add dimensionality to the problem, right? Again, you sort of are familiar with that from the idea of how the energy levels for atoms look, because you've got various quantum numbers involved in those, and that gives you this part where you know, there's some uncertainty at times as to which state might come next. If I wanted to look at what these wave functions look like, it's harder, obviously, than it is for the one-dimensional case. I did find these figures someplace which are wave functions and probability function for this one would be the both n's equal to 2 state for the two-dimensional box, right? And if I look at that, what I've got is if I take a slice along this, if I slice along here or slice along there, I will get something that looks like what we saw for the one-dimensional case, right? So this is with n equals 2, that says my probability function will have 2 maxima to it, right? So if I look along there and just look at the side view, I'd see something that looks more or less like this, which is similar to what I got when I took my, my one-dimensional case, right? Over here, if I look at this from the side, I've got a sine wave on this one and a sine wave over here, right? And so I've got the same sorts of things going on as I would. You can make a three-dimensional box. Trying to visualize the wave functions for the three-dimensional box is in fact rather daunting. If you're interested in this sort of thing, if you search online, you can find various things that there's animations, there's gosh, there's one of those simulation things from the Wolfram Alpha people that will let you play with sliders and adjust the quantum numbers and look at what some of those things would look like. I did include, I guess, just an equation here for the equations for the wave functions and the energies for a particle in a three-dimensional box. This one just now has what? It's got 3 different lengths. A, B, and C are the lengths in the X, Y, and Z directions. It's got 3 quantum numbers, 1 for each direction again. And so as you might imagine, this problem is going to be significantly more elaborate with regard to degeneracy, right? I'd have one state at the bottom where all of the quantum numbers were 1, but then I'd have a set of 3 that had one of the quantum numbers being 2 and 2 of them being 1, and so on as it goes up, right? So my degeneracies would vary between 1 and 2 and 3 as I went through the different energy levels. And so it's a more complicated looking set of energy levels for that particular problem for sure. The last little bit that I'm going to talk about related to the particle in the box in our main content here is about what happens if the walls of the box are not infinitely tall, right? We constructed the original box by saying that there was no way for the particle to get out. It didn't matter how much energy it got, it was in there and not getting out. That's not physically realistic, right? If I think about a molecule, if an electron in my molecule gets enough energy, it can escape. I can ionize the molecule, right? I can ionize an atom. And so the barriers involved in real systems are not actually infinite. So we're going to take a quick look at how this would influence the system, okay? How it would influence what happens in our model for the particle in a box. The math for the finite wall case is a bit more daunting, and so we're really just going to sort of sketch out what some solutions would look like and not get too far into the weeds of justifying everything that shows up. So what happens here is you sort of have regions, okay? You have 2 regions that are outside of the box, right? If I keep my coordinates so that I'm in one-dimensional box and my box is set between 0 and L, right? Then I have the energy goes to whatever V is for regions outside of the box, what are marked here as region 1 and 3 in that designation, right? And so the potential energy there is, it's not infinite, but it's above 0, right? There is some energy associated with being out there. The potential energy is still 0 inside the box, as long as I'm in the central region, region 2, which is X values from 0 through L, right? If the energy is less than the potential energy, the particle is confined in the box, meaning if the energy of the particle is less than the energy that it takes to climb over the wall, then the particle is stuck there, right? If the energy gets higher than the wall, then the particle would actually be able to escape and get out from the box, okay? What happens if you actually figure this problem out is you get wave functions that, that look like this, okay? I still get a ground state wave function down here, which has some 0-point energy. From this one, if I went to another energy level, the next energy level up, the n equals, 1, 2, 3, 4 energy level here, that would be somewhere up here, meaning in that case, the particle would just get out of the box, right? Meaning if it started going in one direction, it would have no reason to come back because it no longer, its energy is higher than what it takes to go over the wall. One of the things that's really fascinating about this is if you look at these sketches, you can see that there are, in all cases, some extent of the wave function that penetrates into the wall, right? And so it is possible for the particle quantum mechanically to get into a region of space that classically it seems like there should be no way to get there. Right? That essentially says the ball was rolling back and forth between two walls and it just decided to roll into the wall a little bit on one pass going over there, right? So this is a truly peculiar effect that happens quantum mechanically for this case. It also leads to something that is a fascinating sort of behavior, and that is if I picture this, imagine what would happen if instead of having this wall is now finite in height, right? But suppose it was also finite in width. Suppose I said the potential energy, the wall only exists here, right? And similarly on this side maybe, right? So if I make my wall have finite thickness as well as finite height, then I open up the possibility of something that is known as tunneling happening. All right, and essentially what happens there, if you look at this, this says now the wave function has some probability of being in the wall here, and in fact, it now has some probability of emerging on the far side of the wall. Right? That corresponds to saying that the particle can in fact escape from the box without going over the wall. It can, well, tunnel through the wall. All right, and this is gosh, at one point, when I first learned about this, it was mostly just sort of an esoteric thing that people talked about in quantum mechanics books and what have you. It now has a number of technological uses, one of which is the so-called scanning tunneling microscope, which you've undoubtedly seen pictures in chemistry books that are images of atoms, either the structure of atoms laid out at the surface, or more playfully, various little cartoon things that have been drawn by putting atoms in place and then imaging them, where people draw assorted stick figures and characters and things like that, okay? And all of those things work because of tunneling. There also are, there's an electronic component, which is sometimes referred to as a tunnel diode, which is based on this behavior. And a few other things like that, right? And all these things happen because quantum mechanics opens up the possibility of things happening that are classically forbidden to happen, right? The tunneling materials, tunneling ideas are kind of fascinating. Your textbook talks about a couple of applications. I haven't decided yet. I may actually make a short video that talks about some of that. If I do, I will label that to show it as essentially just sort of optional extra content. It's a bit too esoteric to think of as something that I'm gonna test you on or anything like that. But it is kind of just some neat ideas, and for anyone who's just interested in some of the quirks that happen mathematically, it's kind of an intriguing topic. And so I probably will try to post a video in which I at least briefly comment on some applications of tunneling. Thanks.